Вы знаете, мне кажется, что все-таки действительно нет ни одного англоязычного человека. И я, может быть, поговорю немножко по-русски, потому что если кто-то запишет и потом будет смотреть, в чем я сомневаюсь, и не поймет, то, может быть, это будет encouraging учить русский язык, но неважно. В общем, я хочу сказать, что я очень был рад принять это приглашение, потому что Вадим Александрович действительно сыграл очень большую роль в жизни каждого из нас. И, собственно, даже, может быть, я непосредственно с ним не работал и не так много обсуждал, но он был один из руководителей семинара по статической механике, одним из 4, я не знаю, мушкетеров. Вот это был, значит, Добрушин, Синаев, Минлос и Малышев. К сожалению, только один остался сейчас в живых, Синай. Вот. И этот семинар, он был действительно очень исключительный, потому что на этом семинаре как бы создавалась новая наука тогда. И это очень всегда exciting, очень интересно, когда на твоих глазах создается новая наука. И так мы как бы входили в статистическую механику. Вот. У меня был еще один такой как бы экспириенс в институте Ландау, когда создавалась конформная теория поля. Я в ней не участвовал, но я видел, как это делается. В общем, Вадим Александрович был интереснейший человек и сыграл большую роль. Он был достаточно веселый человек. И вообще, я хочу сказать, что он был еще, он как бы единственный из участников семинара, кто стал читать работы Глима Джаффа и рассказывал нам про их вот подход к конструктивной теории поля по размерности 3, что безумно трудно. По-моему, это сейчас никто не делает. Это действительно требует большого мужества вообще во все это входить. И Вадим Александрович читал и понимал, и рассказывал нам это. И это было удивительно. Вот. А часто вот там он что-нибудь рассказывает, а его спрашивают, а где это написано? А Вадим Александрович всегда отвечает, а везде. Вот такой вот всегда мы потом стали это даже использовать сами, такую вот фразу, а везде. Хорошо, я перехожу к своей теме. Я назвал ее First Passage Percolation для Product Type Random Environment. И давайте я расскажу, что это такое. Значит, я начну с понятия направленный полимер или директор полимер. Вот у меня слайды по-английски, так что, наверное, ничего. Значит, в самом общем виде это, ну, может, не самый общий вид, но в решетчатом случае, значит, у меня есть решетка ZD, и это space, решетка на пространство определяет, и решетка Z1 – это время. Вместе это ZD плюс 1. И в каждой, это то, что называется disordered решетка, то есть есть беспорядок там, и беспорядок задается потенциалом. Я его обозначаю Xi от X and I. В каждой точке вот этой решетки ZD плюс 1 сидит случайная величина. Вот. И это поле, совместное поле этих случайных величин, есть традиционное инвариантное случайное поле. Вообще говоря, не обязательно независимые, но часто независимые ID случайные величины. Вот. И дальше вот этот потенциал как бы фиксируется, и в нем изучаются полимеры. Полимеры – это траектории случайных блужданий. В простейшем случае я буду рассматривать случай nearest neighbor, случайные блуждания, которые перескакивают ближайших соседей на решетке. Я обозначаю гамма-n. N – это время этого случайного блуждания. Оно, значит, от 0 до n время меняется. И я пишу, что это lazy, это ленивое случайное блуждание. Это означает, что можно перескакивать, а можно и не перескакивать. Можно остаться в той же позиции. Вообще, я считаю, что это более естественный объект для рассмотрения, чем обычные случайные блуждания, потому что тогда нет плюс-минус вот этой вот дихотомии, вернее, четной, нечетной, которые очень иногда несущественно мешают. Ну и к тому же это скорее относится, если вы думаете о случайных блужданиях с непрерывным временем, то это более адекватно описывает ситуацию. Значит, вот гамма-n – это бывает такое случайное блуждание, расстояние между положением в момент времени и плюс 1 и меньше равно единице, но может быть равняться нулю. И тогда можно рассмотреть гибсовскую меру на путях длины n этого вида, а именно взять их и взвесить с весом экспоненция от минус бета на… Да.
Excuse me, can you switch to English if possible?
Absolutely.
Thank you.
Popular demand, I'm switching to English. Sorry,
Zoom
broken
is
English.
recorded
Oh, it's okay, no problem. So the Gibbs measure is, of a particular path gamma n is equal to 1 over partition function, and then the statistical weight is exponential over minus beta, the action of this path, and action of the path an is defined as a sum over all sites visited by this path, so gamma n I, and when you are in this site gamma n I, you take this value of psi and you take sum of them. So you kind of visited sites and take the sum of the values of potential. That's the action of your path, and that is a Gibbs measure. Zn is just a normalizing factor, partition function, to make probability of all paths equal to 1. While the notation omega will be, it's a part of probability space which determine the random variables psi xi. So when I fix omega, it means that xi's are fixed. So I will be kind of in quench situation when I fix disorder first and then consider statistical mechanical problem. All right, so next I would say if beta is equal to plus infinity, which corresponds to 0 temperature, then this is a problem of first passage percolation, because this Gibbs measure just sits on a particular path which is argmin, which is minimizing the action. So there is almost particular path minimizing the action. If we assume that random variable psi have continuous distribution, it's just one path. And the value of this minimizing value, I denoted an bar, that is of interest for me as well. So the main problem in this type of question is to understand the asymptotic behavior as n goes to infinity of this object, either partition function, basically logarithm of partition function, or the polymer measure itself, how it behaves, how it concentrates on which kind of path, or what is how the optimal path in terms of fast path percolation at 0 temperature look, gamma bar, and what you can say about random variable, which is an bar optimal action. So they're all random variables because they depend on omega. And so particular very studied example and very interesting example, which still has many open questions, it's KPZ problem, which Senia mentioned. That's happening in dimension 1, and I will consider dimension 1 as well. And when psi are assumed to be IID random variables. And there is no, you basically should not consider two crazy random variables. You should assume that certain number of moments exist, but basically there are no other assumptions. It's just any distribution of psi will do. And even probably if they're not IID, but with certain decorrelation on distances in space, on times, it also should be the same phenomenon. And prediction of the theory, which is proved for particular models, but not for all of them, and universality is still a very much open problem. The prediction is the following: that the gamma, the path gamma, fluctuates. So the position of this plus gamma, and gamma starts at the origin at the initial moment of time. So at time n, you will find it on the distances. It will be in a random position, but on the distance of the order n to the 2/3, and this is one of the 2/3 Senia mentioned from the origin. The action itself will be proportional to n, because it's sum of n random variables. So it will be some non-random constant c times n, and fluctuations which are of main interest will be of the order n to the 1/3. It's another exponent of KPZ. And amazingly, in this type of problem, it doesn't matter. You can consider positive temperature or 0 temperature, and behavior will be still the same. So if you take logarithm partition function for particular beta, it will be some constant depending on beta, non-random time n, and again, fluctuation of the order n to the 1/3. And what is even more interesting, and this also was mentioned by Senia, that if you subtract the Cn or C beta n here and normalize by n to the 1/3, you would converge to universal laws. And this universal laws in this particular case will be Tracy-Widom law of GUE Tracy-Widom law, exactly the same which Senia considered and defined through random matrices. So this was proof for particular models, but not for all, and universality is basically open problem. Now, the problem which we consider, and it was some time we were considering it, but recently we had some significant progress, and that's why I decided to talk about it. It's also in dimension 1. It is still beta equal to plus infinity, so it's first passage percolation. So I'm interested in optimal paths, but psi are not exactly independent. they have product structure. This is some f on x, which is IID random variables depending only on space coordinate, times b on I, which depend only on time, and this is random sign. So f on x, it's IID random variable. We assume they have compact support, and they have continuous distribution, they have density. B on I are IID, taking values plus minus 1 with probability 1/2, so it's exactly random sign. And we also assume that f on x and b on I are independent. So that's the setting which we want to consider. So in certain sense, you can think that you have realization of potential f on x at certain moment of time, and then every moment of time you either multiply it by +1, which is not changing it, or -1, and you do it randomly. So that's the model which we want to consider. And the people who considered it is, we started it some time ago with Yuri Bakhtin, and then my PhD student, Jeremy Volz, started to work on it, and we understood many things about it, but not all. And then recently, very young Hungarian mathematician, Andras Mazeras, got involved, and we get some progress. By the way, Jeremy Volz, after defending his PhD, has important musical career as a singer and songwriter in Toronto. So he's not doing mathematics anymore, but you can Google him, Jeremy Volz Toronto, and you will find his webpage, manager, whatever. So he's quite successful. Right. So that is a density of f of x. So it's I assume it to be symmetric, plus minus symmetric, but it's not essential. So it's on a compact support between c and minus c. And I can consider density which is not vanishing at the endpoint or vanishing with the endpoint. Both cases will be considered here. So first, let me talk about something which is well known. This is like a law of large numbers. This is shape function. So what is a shape function? So consider problems which we discussed before, but we assume that the endpoint at n is fixed. So you still want to optimize, but with a fixed endpoint, which is n alpha apart from the origin. And alpha is a parameter. So then the minimum of the thing were denoted a and omega alpha. And of course, you have to take integer part. And the standard lemma says that the limit of a and omega alpha divided by n exists. This limit exists, it will be negative. And so I want to have function g on alpha positive, so I put minus sign here. So this is a subadditive ergodic theorem. This is a continuous function, actually convex function on alpha. It's also part of subadditive ergodic theorem. And this is pretty simple statement. It's very conceptual and very general. And all kind of these random setting problems, this law of large numbers can be proved, but usually by means of subadditive Kingdom's ergodic theorem. Now, the second thing which will be important for me is to understand what is called discrepancy of a bond. So if you have a bond, and bond when in one-dimensional relation, so the bond is vertical here, space is vertical, from x to x plus 1, and I denoted E. So what is discrepancy of a bond? So the best thing for past to do is to come to a situation where the value of potential at one point is close to C, and another point is close to minus C. It cannot reach exactly C and minus C. It happens with probability 0, but it can be very close to it. So D on E discrepancy measures how close it is that one of the values is close to C, another to minus C. So it's 2C minus the difference between f at x plus 1 minus f at x value. This difference is always positive. And the smaller the value, the better is for pass, because what pass can do, if you reach, it means that at say point x is close to C and here to minus C. So you sit here when B is negative, and you sit here when B is positive, and then you accumulate almost minus C every time when sitting there. So it's very beneficial for you to be on sites where D on E, on bonds, where D on E is small, but you cannot do it very often because you have to do certain, sometimes you have to find such bonds first of all. So it's exactly small means that either f of x plus 1 is close to C and f of x to minus C, or vice versa. As I said, the optimal path wants to stay on bonds with small value of D, jumping from the site with value close to C to the site with value close to minus C. Now, if you take into account, you will understand that when alpha is equal to 0, so the endpoint is not prescribed to be far away, the path can go to some place where discrepancy is very small. Stay there, jumping depending on B to one or another, and then go back to where it should be. And here it accumulates almost C every time. So the total energy will be minus Cn. If you divide it by n, then this shape function will be close to, the energy will be minus Cn, divided by n, it will be minus C. But since G is with negative sign, so this should be positive, I'm saying that G at point 0, alpha equal to 0, is equal to C, exactly. And another thing, if you take alpha equal to 1, then the path has to go to n. So it's just ballistic path, and then it's sum of independent random variables, and it's order square root of n. So divided by n, it will be 0. So you know for sure that this shape function f on alpha, g on alpha, is equal to C at the origin and 1 so here is what we know about this G alpha. It is C at alpha equal to 0 and 1, and 0 at 1 and minus 1. It's symmetric with respect of alpha. And right. And here, this picture, the other picture shows that what would be typical behavior of pathways when alpha n is kind of giving to you. So then you go, you find the best discrepancy side between 0 and alpha n, then you stay long time here, and then you go to the prescribed point you have to go, and that would be typical behavior. And you want to understand where this point is and how long you stay and stuff like that. So the first theorem which we proved is the following, that G alpha is, in fact, it's tempting to think that this is just linear function connecting the thing, but it is not. It is always above, so it's coincide at this point, but it's above this linear function. So it is non-linear function, it's first statement. And second statement, say that there is a phase transition in this problem. So that for alpha small enough, this is the linear function, and then it starts to be non-linear. So, so there is transition in parameter alpha, which transition which says that linear behavior become non-linear after this critical value of parameter alpha naught. Now, actually, to prove the theorem, we are in situation B. We need to use the fact that density vanishing at the point, but numerics show that it should be true also for situation A as well. But at the moment, it's not, we didn't prove it. There are some technical difficulties proving this. This is first theorem. And second theorem says the following. Let's understand how the path would look like if you are not, say, prescribing at the end point, the other end point, but you say the path is of length n. So then the path will go, reach certain place where it has very ln, where there is a small discrepancy, and then stay here. And if you want to calculate what is the order of this ln, how far you go, then you can easily, it's a little calculation, but trust me, it's a very simple calculation. It says the following, that the optimal behavior will be if ln will be order n to the 2/3. And that's answer to what Seniak question put as a question, whether all 2/3 are KPZ. No, here it's not KPZ, but it's 2/3. So what's happening, that the ln will be order n to the 2/3. Now, since there are n to 2/3 bonds here, you can achieve here discrepancy of the order of 1 over n in power 1/3, because you have to this discrepancy here and here in both endpoints. So probability will be 1 over n to the 2/3. And that is what is achievable if you are this distance. And then if you calculate the thing, and you will say that you will have find the ln, which minimizes the following functional. Some constant C1, which is written here, plus 1/2 discrepancy of ln time n. So the balance is when this ln would be of the same order as this term. And as I said, d will be 1 over n to the 1/3 and ln to the 2/3, and then the balance is achieved exactly there. Now, so in a sense, if I subtract the non-integer, not interesting Cn factor here, I will have to minimize the thing. I mean, have to minimize this expression where n to third was factorized from here. And so I have ln, which is kind of discrepancy divided by n to the third. So distance divided by n to the third is order 1. And this is also order 1 because d is order n to the 1 to the third. And then the next lemma is the following, that if I consider the following thing, I consider a rescued point process mu n. So k are all points of a space, it's a space point. And at every point of k, I would record coordinate k divided by n to the minus the third, and discrepancy on k divided by n to the 1/3, or multiplied by n to the 1/3. And I'm saying that if I take limit when n goes to infinity, it converges to a Poisson process with density not dx dy, but ay dx dy, where a is a particular constant. I'm here consider a situation where density is not vanishing in the endpoint. So what's happening is that most points will not be observable because if delta decay is order 1, then this point goes to infinity. And if k is say order 1 as well, then this point is not visible. So basically, you will see only points which have order 1 contribution of this thing. And it's rather easy to prove that what you will see in the limit, these red points will be Poisson process. And what we want to minimize is the distance between point xy and the origin, which distance equal this c1 absolute value of x plus 1/2 y. This expression we had in the previous picture. So that lemma kind of describe you that how the optimal path would look like. So it would look like, again, it reaches this special place and then stay there. And then you can calculate what will be the kind of Tracy-Widom distribution in this.
Sorry, what is P of C? P is a density. Okay.
P of C there, it's a derivative of the density at the one of the endpoints. Yeah, it's a particular constant. So it's a little bit not universal, but it's trivially rescaled to universality. And then what you can say that if you take constant time n minus, which is kind of what minus your, so signs here has changed. So Cn is a best you can achieve, but you never achieve it, minus optimal an bar, and divided by n to the third, it converges to, in distribution, to random variable eta, which is the smallest distance to the origin for points of the above Poisson point process. And distance was described. So if you do a little calculation, it's trivial calculation, you will see that the density of the random variable eta, so this is what is called Tracy-Widom law in this situation, would look like x squared e to the minus tau x cubed dx, where tau is a particular constant. So you will have pretty universal behavior with this very kind of fast decaying tail and pretty universal behavior here. Now, I must say that there are many open questions here still, which it's still in a kind of work in progress, and how we don't know really how to describe the geometry of the path when it goes to the optimal place. How much time it spends on the other side bonds, which have small discrepancy, but not as small discrepancy. So basically, the idea is that when you reach certain bond, there is a local time spending there, which depends on the discrepancy, but we haven't proved it. And second thing I want to say that this model allows you to discuss several statistics. You can fix realization of disorder in X, and then see what is the statistics in choosing different B's. And then it happens that it turns out that the variance of the optimal action when configuration in X is fixed, depending on B, is extremely small. And I don't have at the moment explanation for that, because it's sum of n random variables, or say large number of random variables, but variance is very small. So it means that when you change the configuration of plus minus signs, and you try to find optimal way to connect to the same point, then the value of action will very little depend on this, on the choice of B. It will be almost the same. So what we see is the variance is just order 1 for very large values of time. And currently we cannot explain this. It's kind of look a little bit. There is some ideas how it can be explained, but it's a little bit mysterious at the moment. So anyway, this is a set of problems where many calculations can be done, and it's not KPZ, definitely not, but it has certain KPZ feature, and it has interesting problems of the type of finding optimal behavior of the path, and how basically it is a kind of control problem, how to control your path in a given disordered environment to get the best results, and how you should behave depending on the realization of your disorder. And that is a problem which is not completely understood yet, but we're continuing working on it. And let me stop here.
Oh, thank you very much. Let's start. Very interesting talk, and please questions.
What's the question?
Please, Tatiana.
Thank you. Here, this scaling 1/3, does it follow also from diffusion approximation? So is it due to fact that there is a diffusion part there? Or you said that it's probably different?
No, I don't think it is. It's a little bit. It's a balance between. No, no, it's not part of diffusion. So these parts are behaving in a kind of not diffusive way, and so the a little bit hard problem to understand how you really have to control the thing, because the naive idea that you just go ballistically to the best possible place and stay there and then go ballistically out, it's not true. You will not go ballistically, you do it in a smart way. And what is a smart way? That's not so easy to say. By the way, this 1/3 and 2/3, it's only when density is not vanishing in the endpoints. If density is vanishing, depending on what is the order of vanishing density, the exponent will be different. I decided to, in this talk, to choose only 1/3 and 2/3 because that is that's closest to KPZ scalings. But actually, you can have here other scalings as well.
May I ask then shortly? So you do know some other functions which would give another scaling?
Yes, if density depends on the
thank you.
density of the disorder of the thread available.
Thank you. So that's not universal to the model. It reflects your density function.
It is if density is not vanishing at the endpoints of the compact support.
Thank you.
You're welcome.
Some other questions? Thank you once more. Thank you very much.
Yes, thank you very much for having me. And unfortunately, I have to kind of disconnect now because otherwise they will kick me out from the hotel. But thank you. Thank you very much.
Thank you very much.